So this is a related rates problem. You have a 13-foot ladder that's leaning against the wall. You can see it on a picture here. This is the ladder and this is the wall it's leaning against. You have Jack who begins pulling the foot of the ladder. So Jack is pulling this extremity of the ladder away from the wall at a rate of 0.6 feet per second. How fast is the top of the ladder sliding down to the wall? Sliding down the wall when the foot of the ladder is 5 feet from the wall. So we're asking several things here, and for these questions you always start by naming the quantities you're being asked about, right? So if I say that the height of the top of the ladder is y and that the distance of the bottom of the ladder to the wall is x, this here would give me a right angle because we're assuming the wall is straight up, standing straight up. Using a Pythagorean theorem on this triangle, right, you have the square of the hypotenuse equals the sum of the two squares of the other two sides. And that's an equation that combines the two quantities we're interested in. The next thing you do is you derive both sides implicitly with respect to t. T is a variable that's not mentioned here, but because I'm given the rate of change of the foot of the ladder with respect to time, then I'm assuming that x is x of t and y is y of t. So I derive both sides with respect to t. So in both cases on the left side, I'll use the chain rule. So I do power rule first, times the derivative of the inside function, plus power rule first, derivative of the inside function. So that's the chain rule used twice there. And then the derivative of the right side is just the derivative of a constant. The derivative of 169 equals 0. So that's what I have. The next important thing to remember is to remember the things we are told. So we are first of all told that Jack is pulling the foot of the ladder away at a rate of 0.6 feet per second. So that means x is increasing at a 0.6 rate. So this means dx dt is 0.6. So this comes from this. Secondly, because this changes, both x and y change over time, we are looking for a specific moment in time, which is the moment when the foot of the ladder is 5 away from the wall. So when x is 5, what is y? That's the second information we need to plug it into that equation. So we'll say that back from this original Pythagorean theorem equation, 5 squared plus y squared equals 13 squared. So that's y squared equal to 169 minus 25. Y squared equals 144. Y equals to 12. So we now know dx dt. We know y. We knew x already. If we plug all of those quantities in this equation, we will get 2 times 5 times 0.6 plus 2 times 12 times dy dt, or y prime. That's what we want to know. So that in turn gives us 6 plus 24 dy dt equals 0. So that gives dy dt equals minus 6 over 24, which is minus 1 over 4, if you simplify both sides, feet per second. So this means, if you want to fill all of this in, first of all, the equation that combines both quantities is this. If you differentiate both sides, you get 2x, 2y 0, and that the rate of change of the top of the ladder is minus 0.25. They're asking for it in decimals, feet per second. Now, in most cases, they won't ask you to carry this minus sign over. In most cases, they'll say, because we're already saying the top of the ladder is sliding down the wall, the sliding down part is already taking care of the orientation of this. So when we say sliding down, we're already understanding that y is decreasing, so there's no need to include this negative over there on the minus 0.25. So I'll just put a 0.25 feet per second. And that's how you solve this type of question.